Hi, my name is Marko Vukasinovic, and this is my Physics 2212 Lab 1 charge tapes. First off, the purpose of this lab is to understand the electromagnetic interactions between two charged pieces of clear tape. Additionally, we want to determine how much excess charge is on one piece of tape, and we want to use GlowScript to simulate these interactions through coded models. Some fundamental physical principles used in this lab are Newton's second law, gravitational force, and electric force, also known as Coulomb's formula. For Newton's second law, it states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass, as seen here in the equation. For gravitational force acting on an object is equivalent to the object's mass multiplied by the acceleration due to gravity, and it points in the negative y direction. As for electric force, the electrostatic force between two charged objects is directly proportional to the charges of the objects and inversely proportional to the square of the distance between them. Here in the equation, Q1 and Q2 are each point charges, while r is the distance between the point charges, and K is Coulomb's constant, which equals 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. Before we get into it, here's a quick preview of the results. I found that the clear charge tape has a positive charge. When two pieces of tape are placed near each other, they repel each other, which would be expected by Coulomb's law, stating that like charges repel and opposite charges attract. I found that a single piece of tape has a positive net electric charge of 1.208 e to the negative 8 coulombs. Moving on to the procedure of the model, I taped one piece of tape to another piece that was already taped down to a desk. By quickly pulling the upper tape off of the base tape, I made a charged U-tape and repeated this process to make another one. I made notes of the length and mass of the tape. Next, I observed the interaction between U-tape and a negatively charged plastic pen to determine the charge of the tape. From there, I placed one U-tape on objects of equal heights as shown in this lower model to the left. This piece of U-tape would act as the system. Next, holding another U-tape below, which represents the surroundings, I slowly raise it towards the hanging U-tape to observe the interaction between the two U-tapes. I made note of the separation distance, and one began to float. However, in this model, I made some assumptions. The model assumes that each piece of tape has the same net charge, which is reasonable because each piece of tape was made by the same process. Each piece of tape is treated as a point charge located at the center of the piece of tape. And while these assumptions may result in calculations that are not precisely accurate, they simplify the calculation process and allow us to demonstrate the fundamental ideas of the lab. I made note of the initial conditions of the lab, length, width, and mass of the tape, and I found that separation distance when one piece began to float was 0.025 meters. The interaction between the U-tapes and a negatively charged pen was attraction, which meant that the U-tape must be positively charged in accordance with Coulomb's law. Next, the interaction between two U-tapes in the model was repulsion, which should also be expected because as the tapes are effectively identical, they should repel. To calculate the magnitude of gravitational force on the floating tape, I used the formula shown earlier, which I found to be 0.0021 newtons. Because the floating tape is stationary and acceleration is zero, net force must be zero, meaning that the magnitude of electric force must equal the magnitude of gravitational force, and the magnitude of electric force thus must be 0.0021 newtons as well. To calculate for the electric charge of the floating tape, I rearranged the formula for electric force for Q. From there, I plugged in my values and found that Q equals 1.208 e to the negative 8 coulombs. Moving on to the coding, in part 1, the objectives were to model the pieces of tape as point charges and estimate the amount of charge on each tape necessary to float one piece. As shown here in a screenshot of my model, the two pieces are floating above one another with gravitational force pulling down and electric force pulling up. The model found that the charge of the tape is 1.19609 e to the negative 8. In part 2, my objective was to model the pieces of tape as a line of charges rather than a point charge, and to calculate the electric force and gravitational force. My model, shown below, shows this line of charges by the green arrows pointing up. The model found that the magnitude of electric force was 2.0548 e to the negative 3, and the magnitude of gravitational force was 2.0601 e to the negative 3. The model's calculated values lined up pretty well with the calculations that I did myself, although the computer produced more precise values, as should be expected. However, the model's values for electric force and gravitational force were not exactly equivalent as they should be. This could be explained by a rounding error in the model's calculation for electric force over the summation process. If the signs of electrons and protons were flipped, The observations that I made in my lab would remain the same because Coulomb's law would still hold true, maintaining that like charges repel and opposite charges attract. However, the directions of electric fields and forces would be flipped, as a formerly positive charge would now act as a negative one, and vice versa. Finally, there were differences in the calculated Q values for the point charge and line charge model due to differences in location and concentration of the charges. Overall, the line charge model is more realistic because charge is dispersed along the tape, likely providing a better estimate for Q.